Hello everyone, welcome back. In our previous videos, we understood about what is binary tree, and we also understood about the different traversal techniques to visit all the nodes of binary trees. In this video, we will cover about the insertion and deletion process, where we will understand the different ways to insert a new node or delete the existing node from binary tree. So let's start. Insertion in binary tree. So these are the four different ways using which we can insert a new node into the binary tree. Now there is no fixed answer which way to insert a new node we should use. It depends on what type of problem we are solving, and whichever way to insert a new node in binary tree is suitable for solving that problem, we can use that way. Let's understand each way in detail in next slides. So first way to insert a new node in binary tree is insert at the first available position. So we traverse the tree level by level here using queue. So we visit the level 0 nodes, then we visit the level 1 nodes, and then level 2 nodes, and so on. Like then what we do, basically we find the first empty spot. So when we are traversing the nodes level by level, we check what is the first empty slot in that level. It can be either left or right child. So for example, in this case, this is the empty spot, right? In this level 2, this is the first empty spot. So we can use this empty spot to insert a new node. So it is basically inserting at the first available position. So this type of way to insert a new node helps to complete the tree rather than making the tree as a skewed tree. So this is useful in a scenario when we want to make sure that tree is all the empty slots of the tree are utilized before actually moving to the next level. Now let's understand the implementation of this way to insert the new node. So this is our class structure which represents the node. It contains the data and left and right children node pointers. Insert level order. So because we need to visit all the nodes level by level. So let's understand. So when we insert one, basically root is null. We don't have any tree. So we'll create a new node and assign it to the root and return. So root is pointing to one node now. Then next, when we insert two, basically we go in this while loop. In a queue, we add one, and there is no left child to the one. So we insert a new node to the one. So when we insert three, similarly, we basically again start from the root, which is one, and continue till the queue has some nodes to process. Basically, continue till we process all the levels and we find the first empty slot. So you can see if we find that the left child of the node is empty or null, then we can use that as a first empty slot and create a new node there. If right child is empty, then we can use that right child slot to create a new node. So whichever is the first available empty position. And we continue this for each new node. We basically traverse from root for each node and insert at the first available position. So this is the implementation of inserting the new node at the first available position using level order implementation. Now the second way to insert new node is insert at the leftmost available position. It means that, so let's understand with the code example, insert leftmost. So when we want to insert one, we check, basically node is null, so we don't have a root yet, so the root will be created, which is 1. Then when we do insert 2, it will basically come here that node left is equal to null, so it will assign the left child. So basically because we are inserting at the leftmost available position. And when we insert 3, it will again call this insert leftmost method with node 1, and then it will go to the else condition because left of the one is not empty or null, so it will go and then recursively call the insert leftmost with node 2 as a root or node. And for node 2, left is null, so 3 will be inserted as a left child of 2. Similarly, same process is followed for each new node. So as you can see, the tree is skewed tree. It means that it is not utilizing the empty positions here, like we saw in a first way to insert, basically inserting at first available position. So it can be useful in a case when we want to prioritize the left childs. But if our requirement is to make the tree less heighted or not skewed, then this is not the suitable way to insert the new node. Similar to leftmost available position, the next way to insert new node is insert at rightmost available position. So the implementation is kind of similar to the previous way to insert, but we, instead of checking left child, we check for the empty right child. So when we insert one, there is no root, so we create a root which is node 1, and then when we insert 2, basically the right of the node 1 which is null, that's why we create a new node and assign it to 2, basically the right child of 1. Then when we insert 3, now it will go to the else condition and recursively call this insert rightmost with node 2 as a root or node, and it will then assign or basically create new node for value 3 and assign it as a right child of the node 2. Similarly, we can follow the same process or call this function for every new node which we are inserting, and that function will be called with node 1 as a starting node and continuously or recursively check for empty right slot. So again, you can see in previous way to insert at leftmost position, we can see it was skewed, and this way also when we insert at the rightmost available position, the tree is a right skewed tree. Again, when we want to prioritize the right side of the tree, then this is useful in some of the cases, but if you want to utilize the empty slots of the tree, then this is not a useful way to insert the new node. Next type of insertion is insert at specific position. So it is not necessary that you follow the insertion way to insert at first available position or insert at left or right position, etc. You can insert at specific position also. For example, if this is our input tree, if you want to insert 6 as a left child of 2, then we can do that also. But in that case, we need to assign the left child of 2 to the left child of, basically as a left child of 6. So previously 4 was the left child of 2. So when the 6 is inserted, 6 became the left child of 2 and the left child of 2 became the left child of 6. So this adjustment we need to do based on where we are inserting or at which specific position we are inserting. Sorry for this spelling mistake, it's an insert. Let's understand the deletion process in binary tree. So whenever we delete any node in a binary tree, we need to handle these 3 cases. So for example, the first case is we are deleting the node which is a leaf node. For example, these nodes which don't have any children. The next case is the node which we are deleting have only one child. The node, if we are trying to delete, if it has only left child or right child. Deleting a node which have 2 children. For example, if we delete node 1 or node 2, they have 2 children, right? So for each case, we need to handle the delete logic separately. So let's understand the delete logic or deletion process logic for each case. So the first case is the node which we are deleting is a leaf node. For example, if this is our binary tree and we want to delete a node with key 5. So we will delete that leaf node directly, and if that leaf node is a right child of its parent, then assign the null to the right child of that parent. If the deleted node is a left child of the parent, then assign null to the left child of the parent. Let's understand with the code. So we have implemented this delete method. If we see that the node data matches to the key which we want to delete, then we are handling 3 cases which we discussed in previous slide: deleting the leaf node, deleting the node with 1 child, and deleting the node with 2 children. And then we are going for left and right subtree. if we don't go into this if condition, to recursively check for the node which is matching with the key value. So let's understand. We will call this delete method with root of the tree, which is 1. So that function call will go to the system stack, because whenever we do the recursion or make a function call, that function call entry is added to the system stack. So delete 1 is added to the system stack. Then for node 1, we are going for a left subtree, because it will not go to the if condition, because we are deleting the node with key 5. So it will go to the left subtree, which is 2. And for 2, it will go to the left subtree, which is 4. And for 4, the left child is null. So it will basically come back from this condition, which is a base condition. If node is null, return null. So it will come to the previous execution, which is for node 4. It will assign null to the left of node 4. It will go for right subtree, which is also null. So it will come back and assign null to the right side of the node 4, and we will return the node 4 to the upstream. Now it will go to the previous execution, which is node 2. Now it will come here. It will assign left of node to the node 4, which was returned in a previous function call, and it will go to the right subtree. So the right child of 2 was 5. So it will call the delete method with 5 node, and it is matching with the key. Now the node 5 is a leaf node. So what are we doing? We found the node with key value. If it is a leaf node, we are just returning null. Basically, we are detaching that node 5 from its parent. How? We are returning the null. So it will go to the previous function call, which is delete function call with node 2. It will come here. That function execution will come here. So node.write, it will assign a null, because we are returning null here. So it automatically made the right child of node 2 as a null, because we deleted the node 5, which was right child of node 2. That's why we made right child of node 2 as a null. And we come back from the execution and finish the execution for deleting the leaf node, which is 5. So let's understand the second use case, which is deleting the node with only one child. For example, if we want to delete a node 2 here, which have only one child, which is left child 4. So what we do, we delete the child, but before deleting, if this child is a left child of its parent, then we assign the child of deleted node to the left child of the parent. Or if the deleted node is a right child of the parent, then we assign the child node of that deleted node as a right child of its parent. Like this, we deleted the 2 and we assigned its left child as a left child of its parent, because the node which we deleted was a left child of its parent. Let's understand the code. So same delete method. Now when we call this method with now we'll come to this delete node with one child logic. Let's understand it. So when we will call the delete method, we'll call with node 1, and the key is 2 here, because we want to delete node 2. So for node 1, it will not go to the if condition, it will go for left subtree, delete node dot left. So the left child of 1 was 2. So left child of 1 was 2. So it will go to this if condition. So this delete function is getting executed with node 2 as a argument. So node.left, node.data is equal to key is 2. It is matching, so it will go into the if condition. Now it is not a leaf node because it has one child, left child. So it will go to this if condition, node.left equal to null or node.right equal to null. Means one of the child is null. So it will call this delete node with one child. It will come here. Now the node which we are deleting, if it has a left child, then we are returning the left child of that node. And if it has a right child only, then we are returning the right child. So basically now node 2, we are not sending back the node 2 reference. We are sending the reference of its child, either left child or right child, whichever is not null. So when it will return from here, so that function call will get removed, and we'll come back to the previous function call, which is delete function call with node 1. It will come here because it had gone to the left subtree. Now, because we returned the left child of 2 as a reference here, so for node 1, we are storing in a left child the reference of node 4, which was basically the left child of the node which was deleted, node 2 which was deleted. So this is how we are assigning the left child of 1 to the left child of the node which was deleted. So in this case, 4. So this is the implementation for a case where we are deleting the node with only one child. Now let's understand the deletion process where we are deleting the node which have two children. For example, if this is our binary tree and we want to delete a node with key 2, now node 2 has a two childs, left and right. So what do we do in this case? So first thing which we do is, for a node which we are deleting, we check the deepest node in that subtree where the node which we are deleting is a root node. For example, 2, 4, 5, this is the subtree where node 2 is a root. So what is the deepest node? We traverse that subtree level by level. So this is level 0 and this is level 1 and so on. And in the last level, the node which is visited last is the deepest node. For example, this is level 1. This is first level and this is second level, and there are no more levels. So this level is the last level for this subtree with node 2 as a root. So in this last level, which is the last node, the last node in this level is 5. So this is the deepest node. So the deepest node is the last node in a last level for the tree where deleted node is a root. So what do we do once we check the deepest node? Once we find the deepest node, we detach the deepest node from its parent. So we detach, and then the node which we are deleting, the left and right child of that node now become the left and right child of the deepest node. So node 2 is deleted and left and right child of that deleted node are now the left and right child of the deepest node. Why do we do like this? Because if you see, the deepest node does not have child, and if we move that deepest node, it will be less disturbance in a tree structure. So we don't have to handle changing the children's too much by just replacing the deleted node with the deepest node. Let's understand the implementation. So the same delete method where we are checking if we find the node with the data which is matching to the key which we are deleting, which is 2 in our case. If not, then it will go for left subtree or right subtree. Now, let's say when we call this method recursively, delete method is called for root of the tree, which is 1. Then it will not go to the if condition, it will go for left subtree. So left child is 2. So it will call the delete method with node 2. So node 2 has a 2 children. So it will go into the if condition because it is matching with the key which we want to delete. It is 2. And it will call this delete node with the 2 children because node 2 has a 2 children. Let's understand the implementation of this. So the delete node with 2 children. So what do we do here? We first check the deepest node. Find the deepest node and detach it from its parent. Let's understand implementation of this. So as we saw, we are checking the deepest node in a tree where the deleted node is a root. Basically the subtree where deleted node is a root. So we iterate using level order, and when we are iterating, we are maintaining the parent node as well because we want to detach. So the last node also, we are basically, the last node is nothing but the deepest node because that will be the node which will node which will have the reference to the last visited node in a level order traversal. It stores the last node, and we are storing the parent of the last node. So once we go to the node 5, let's say we got last node as a node 5, as we saw in a diagram, the parent of it is a 2. So if the parent is not equal to null, then if the deepest node is a left child of its parent, then make the left child of its parent as a null. Basically, we are detaching the deepest node from its parent. If it is a right child of its parent, then detach it from the right child by assigning right child as a null for the parent and return the deepest node which we found. Now the deepest node which we found is in node 5. So deepest node is node 5. Now for deepest node, we left and right is nothing but the left and right of the node which we are deleting. So the left and right child of the node 2 will now be the left and right child of the deepest node, which is node 5. And we return the deepest node, which is node 5. Now, you can see, when we can see that this delete node with 2 children, this method will return the deepest node, which is node 5. It will return. So it will basically go back to the previous execution, which is the delete function execution with node 1. And it will come here because the node 2 was on the left side. And now the left children of node 1 will become the deepest node, which is node 5, which we had written from the delete function execution for node 2. So we got the node 5 and we are assigning the left of node 1 as a node 5. And node of right, we go and check for the right subtree to see if there are any other nodes with value 2. If not, then we return the node 1. So you can see how we change the structure of the tree very easily. So whenever the delete function is executing in the context of the node which is getting deleted, if it is a leaf node, we return null. If it is a node with only one child, we return the left child if it is not null, or right child if it is not null. Or if you are deleting the node with 2 children, then we return the reference of deepest node. So for the node which is getting deleted, we return the reference to the previous function execution, which is delete with node 1, so that the left or right subtree of that node will get updated properly based on whatever we are returning for the deleted nodes. So hope you understood about the different ways to insert the node in a binary tree. There are different ways to insert the node in binary tree, but it is not fixed that you should use one of the way. It depends on to the problem you are trying to solve, and you can go in any order, like you can go from left to right or right to left depending on the problem requirement. And also we understood about the deletion process and the 3 cases we need to handle, like deleting the leaf node, deleting the node with 1 child, and deleting the node with a 2 child, and how the logic for each case is handled separately. This will definitely help you to understand the basic knowledge about how the insertion and deletion works in binary tree. If you like the explanation and video, please share and subscribe. Thank you so much.